Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. We're on this AP Physics C, or your engineering physics in college, the mechanics only piece. We're in Unit 2, Newton's Laws. Okay, these are going to be our last two videos on Newton's Laws, and we're going to be talking about center of mass. Okay, so what is center of mass? The definition of center of mass is a point on an object that you can concentrate all the mass to represent it. A lot of times if you were in AP Physics 1, they gave you a meter stick and they said, okay, move your fingers in, and where it balances right above it is the center of mass. And this should be in the middle, as you can see, because it's balancing there. So that's what center of mass is. It's why when we do our free body diagrams, we can make any object a dot, which I love since I am not an artist and I can draw a dot, but everything else, not so much, okay? We're gonna get started here. But as always, AP Physics C is going to go into a calculus component. But before we get into that integral and how we use it to find center of mass, we're going to start with our old AP Physics 1 just to remind ourselves of what that looked like before, when we had this as our equation for center of mass, that the sum of the mass times these distances divided by the sum of the mass equals your center of mass. All right, and you're like, what? All right, I don't know if I remember this or not, so let's just make sure we remember this. Maybe you do, and good for you if you do. I have a 1 kilogram dot here at 4 meters on my x-axis. I have a 2 kilogram object here. I think I said a dot, I meant object, up here at 4 meters on the x and 3 on the y. And then I have this 3 kilogram on the y-axis at 3 meters. All right, I'm going to tell you that I want to know what is the center of mass of this system. Now this is a 2D. We're dealing with x and y, so it's going to have a center of mass in the x, and then it's going to actually have a center of mass in the y as well. All right, so let's get started here. Easiest thing when you see this system is do coordinates, so you don't in your head go, wait, is it 4, is it 3? Just do your coordinates. I'm at 4 and 0 here. I'm at 4 and 3 here. I'm at 0 and 3 here. Now, for your x, just take the mass of the object, which is 1, and then multiply it by your x coordinate, because it's 4 meters here on the x-axis. All right, then I'm going to go to the 2 kilogram, and I'm at the 4 on my x-axis, and then I go to the 3 kilogram, and I'm at a 0. And then I have, that's a 0, that was terrible. All right, then I add up my masses, which is 1 plus 2 plus 3. All right, so that's going to be 4 plus 8, that's 12, 12 over 6, and that's going to be 2 meters is my center of mass in my x. That makes sense, right? Because we're here in the middle at 2 meters. Well, if you look at this, I have 3 kilograms on this side, and I have 3 kilograms on this side, so that makes sense. All right, then I do the y, and I do the same thing. We got to get moving, so we're doing calculus. I'm going to do this really fast. We got to get to that integral part. I have 1 times 0. I'm just taking my y-intercepts now, plus 2 times 3 plus my 3 kilogram times 3 on my y-intercept there. I have, divided by, my total mass, which is 1 plus 2 plus 3. That's going to be 6 plus 9. That's going to be 15 divided by 6. And that's going to be a 2.5 meters. Does that make sense that here's 1.5 is half and I'm way up here? It does, because I have 5 kilograms on this side and only 1 on this side of that center of mass. All right, that makes sense, because remember, center of mass always shifts towards the more mass, right? So I have 5 kilograms up here, so it makes sense it wouldn't be at 1.5, it would have shifted up. Perfect. Well, then that means if I go at 2 and 2.5, that is my center of mass total there in the x and the y. Okay, perfect. All right, now I'm just going to erase that because that was just a review. Now we're looking at this. Now we're looking using an integral. All right. Now I'm going to go ahead and start with the rod. It's basic. The rod with uniform density. And we're going to get started here with this. So what's happening here is I have a rod that has a mass M, capital M. It has a length, capital L. All right, well, I can take, we know an integral is a sum of all the little rectangles that make up a shape, right? It's the area under the curve. If I have this rod, I can take all these little bitty pieces here And if I had an infinite number of them, and they're infinitesimally small, we always love those big words, then I can actually get the whole shape of this rod. Okay, and these little shapes are going to have a width of dx. All right, they're going to have a mass, the little triangle has a mass of dm. Okay, so they've got a little width of dx and they have a mass of dm. And they change in their x distance, right? X meaning the distance from, my marker's about to go, x meaning the distance from my point right here, my origin to where this is. Well, that one's x. This one has a different x. It would be all the way down here would be x. All right, so the x is changing, that variable. But the little dx's are not changing. They're all the same width. They're all the same mass dm. Okay, perfect. Now that we've explained what that is, this is your center of mass equation right here. All right, and then we said this is uniform density. We're going to do another one that's non-uniform in just 1 second. And we're going to be using linear mass density. Most of us are familiar with our volumetric mass density, which looked like this. And we'll use it in the next video for shapes, for rigid shapes. But it's mass divided by volume. It's volumetric mass density. This is linear mass density. All right, that's the one we need to use for these rods. So here we go. But here's my problem. I'm going to go ahead and rewrite this down here that I have 1 divided by the mass of that rod with the integral of x dm. Here is the conundrum of this integral. You can't take the integral of x with respect to mass. You can take mass with respect to mass. You can take x with respect to x. All right, but you can't take x with respect to mass. So we have to find an expression to replace that has dx in it. That is the issue. And so we're going to look. We know that lambda is the mass of that whole rod over the length of that whole rod. Well, that is similar, because we've got similar little rectangles here, to our mass of the little guy. We're looking at our little infinitesimally small rectangles. They have a mass of dm, and they have a length of dx. We called that dx, that little width of them, dx. All right, now I can start manipulating. In physics, this is where I tell my students, physicists are very good at manipulating. We're going to start manipulating this thing so that we can have an expression for dm. All right, so here we go. I'm going to multiply. I'm going to have lambda times dx equals, so I'm going to kind of forget this right now and look at lambda. Let me rewrite that where it says, well, okay, if lambda equals dm over dx, kind of take out this middle part, then I multiply dx over here, and I get that dm is equal to lambda, our linear mass density, times dx. And I'm like, ooh, I have a dx. Okay, this is good. So I'm going to put that in. X, oopsies, I got ahead of myself. X, I'm going to put this whole expression in, lambda dx, and then I still have my 1 divided by mass equals my center mass. I'm like, oh, this is good. I have x in terms of dx. I can do this. And my lambda is equal to the total mass of that rod divided by its total length. So I'm going to put that in. The total mass over the total length is lambda dx over 1 over m. Okay, remember we want to take out those constants, things that don't change out of that integral. Mass of this rod does not change, it's mass. The length of this rod, the total length, does not change. I can take those out. And now I have 1 over mass times m over L. I'm just taking that out, and I'm left with x dx. And that equals my center mass. All right, well, my masses cancel out here. Okay, so you're gone with that. And I have that my center mass is equal to 1 over L x dx. So now I'm going to take the integral of this. Now, where are my limits? We got to remember that. Okay, my limits are from the end of the rod to the start of the rod. So it's going to be L to 0 on that x-axis. Because remember, you're looking, since you're taking it in terms of x, you're looking at that x-axis. And the whole length, we're going from L to 0. So that's going to be L to 0. All right, now I take the integral. I'm going to come up here. And I have that my center mass is equal to 1 over L. And then I'm going to take the integral of this. I'm going to raise that exponent by 1. That's 1 plus 1 is 2. Divide by that. So that's going to be x squared divided by the new exponent. So that's going to be x squared over 2. And I'm going to take that from L to 0. Now my center mass, that's an L by the way, not a 2. I have 1 over L, of course. I have L squared over 2. And if I put 0 in there, 0 squared over 2 is just 0. So I'm left with this. One of my L's cancel out on top and bottom, and my center mass is L over 2. Which we actually knew that going in, right? This is a rod, center mass is in the middle when it's uniformly distributed. Okay, now we're gonna look at this non-uniform density rod. And what does that mean? It means we have a rod, just like we did before, but instead of center mass being at L over 2, right in the middle, mass is actually going to be shifting in this case over to the, center of mass, Center of mass is actually going to be shifting over to the right because we're going to have, this is non-uniform density. We're going to have this end is going to be more dense than this end. So center of mass is going to be shifting to that right. Now, there's some things you need to know. First of all, the mass of the rod is still M. M is still mass of the rod. We still have L as the length of the rod. All right, but now, and we're still going to have the same problem. You can't take X in terms of dm. We're still going to have that same problem. We still have the same little rectangles that have a mass dm and a width dx. Okay, but here's where it differs. Your linear mass density is not going to be the mass of the rod over length anymore. They're telling you that your linear density is now 2 times the mass over the length squared times x. Because, and there's an x in this now, it's a function of x, because as these little rectangles get farther away from the x-axis, then you're going to be increasing your linear mass density. Because look, as x, in this little triangle, x is a short distance from the origin. This triangle, it's a longer distance from the origin. So my x is bigger times my mass of my rod times divided by the length squared of the rod times 2 equals the linear mass density for that little guy. So it's changing as x. As x gets bigger, meaning as these little rectangles get farther away from the origin and x gets bigger, then the linear density is getting bigger. So you can expect that center mass to shift to the right. All right, so we still have the same issue, but now lambda, remember, lambda is not equal to mass over length anymore. It's equal to this equation. Then you do it exactly the same. Instead of putting mass of that rod divided by length of the rod in here for lambda, we're going to be putting this expression in for lambda. But you do it exactly the same way, pretty much. So here we go. We have 1 over m x. I need an expression for dm. All right, so same thing. We know that lambda, we're going to set up this little similar, the rectangle to the rod. Okay, so we have lambda equals 2mx over L squared. Let me put x out here to be consistent, x. But we still have that same rectangle. The rectangle has a mass of dm and it has a width of dx. All right, so the rectangle remains the same here. It's the whole rod's linear density that changes. Okay, now I still need that form. I'm going to pretend that's not there, and I still get lambda dx equals dm. All right, so I took that out, lambda equals dm over dx. Now I just plug that in for dm. I plug in this expression for dm, which is lambda dx. All right, so that's looking good. Now I do like I did before. I'm going to sub in for lambda, but not mass over length. I'm going to sub in my new equation that they gave me, and they will have to give you that. And it may not be 2, maybe 4, maybe 6, whatever. Whatever their expression is, whatever it looks like, you plug it in. All right, so we have 1 over m x. My lambda is 2 mass of the rod over the length of the rod squared times x. Don't forget, we have an x there now, dx. Because that lambda, that linear mass density is changing as x changes. All right, now I'm going to take out all, just like always, I'm going to take out all those constants. All right, so I have 1 over m. Mass of the rod doesn't change, length of the rod doesn't change, and I have x squared now dx. Look, I have an extra, here was x. Where did we get to? Here, x dx. We have x squared dx here because we have this extra x that was in our linear mass density equation. All right, I have a mass that cancels. I'm evaluating this from L to 0 because it's still the length of this thing to the origin at 0. All right, so I have x center of mass equals, those masses cancel. I have 2 over L squared. I'm going to take the integral of that. It's just x cubed. You add 1, divide by the new exponent, so it's x cubed over 3. From L to 0, the total length of that rod to 0 where it's at the origin. So I just took the integral of that. Now I'm going to put L cubed in, so I have x center of mass equals 2 over L squared times, that's going to be L cubed over 3. And then if I go ahead and put the 0 in, 0 cubed over 3 is just 0, so I'm going to not look at that. Confuse ourselves. Okay, I've got L squared on the denominator and L cubed in the numerator. So all but one of those L's cancels out on the numerator. And I am left with 2/3 the length of the rod for my center of mass, and that's where it would balance. And we said it was going to be greater than L over 2 when it was a uniform rod right in the center because we had more mass on this end and it was changing in density. So it's exactly right. We have 2/3 L. All right. That explains how to do center of mass with integrals for rods and non-uniform density rods. That we're going to do one more video on a rigid shape, and we're going to be using not linear mass density there, but we're going to be using volumetric mass density on that one. All right. I hope this helps. If you like this video, please give us a like, subscribe, share with your peers if they are needing help and these are helping you. Thank you for watching and happy physicsing.